All right, good people. We're looking at another example of finding volumes of solids created by cross sections, right? So let's read example number 2 here. R is the region in the first quadrant, so that narrows down my graph. It's only looking at the first quadrant, bounded by the x-axis and the graphs of natural log of x and y equals 5 minus x. Okay, so here's the natural log. And I'm going to go ahead and label that as such. This is y equals the natural log of x, and then this is y equals 5 minus x, as shown in the figure below. The region R is the base of a solid. For this solid, each cross-sectional perpendicular to the x-axis is a square. This sounds familiar. And this was 12 years after the last question that we saw. Write, but do not evaluate, an expression involving one or more integrals that gives the volume of the solid. Okay, so here's a very popular phrase. Write, but do not evaluate, an expression involving one or more integrals that gives the volume of the solid. Well, we're going to start where we started before, which is notice that the cross sections are perpendicular to the x-axis, so everything's going to be in terms of x. We know that our shape is a square, so once again, I'm starting with a square. Let's spell it correctly. And I know that to find the area of a square, I just take the side and square it. So that's going to lead us to the area function of a square, which means if I were to draw a perpendicular cross section to the x-axis, it would look like this, right? Except I noticed that after a certain point right here, now my top function and my bottom function changes. So here's my representative rectangle. And in this part, natural log of x is the top and y equals 0, the x-axis is the bottom. But over here, once it crosses this point, whatever this point is, now the line 5 minus x is the top and this is the bottom. So we're going to have to create two different setups. And so one of them will be, let's do this setup first. Let's do the first part. From 1 to wherever that intersection point is, this is the top, this is the bottom. So I'm going to say, let's color code this natural log of x minus, and then the bottom here is just 0 squared. That's going to tell me the area of any square cross section in this part of the region, right? And then the second part, so I'm going to say or. If I go to the second part, then this is the top and this is the bottom. So this is the top, 5 minus x, and then the bottom would be 0, y equals 0, and then we're going to square that. Now, we'll simplify here in a little bit, but I guess I need you to see, do you understand why we have two separate area functions, right? In the first part, between 1 and whatever this value is in the intersection, natural log is on top, 0 is on the bottom, but then between that pink point and wherever this is this 5? Yes, I think it is. 1, 2, 3, 4, 5. And 5, then that's a separate thing. Awesome. So if we're looking for the volume is, or I said, equals the integral from 1 to whatever this point is, question mark. So I'm going to say 1 to something of natural log of x, and let me just do this in red, natural log of x squared. I don't know what this is though. And then I'm going to add a second integral that starts at that unknown x value that we're going to know here in a little bit, and we're going to go to 5. And in that section, this is my setup. dx. Make sure to put the dx's. The dx's are important because we remind ourselves that even though we're taking a slice and we're picturing the slice to be very thin because we're adding an infinite number of slices, that slice still has a thickness. The dx represents that thickness. Great. This is the setup, except I don't know the intersection point. So I'm going to need my calculator. I get my calculator, and we're going to find the intersection point of those two. So I come over here. Let's clear that out, and we'll do the natural log of x. We'll clear that out. We'll do 5 minus x. And then I believe my window will go from 0 to 5. I'm sorry, from 0 to 5. And then my y min and y max, it looks like it's going from 0 to 2 maybe. We'll give it some room, and we'll go from 0 to 2. Graph it. Here's the first function. Here's the second function. That's the intersection point we want. So second trace, do the intersection, option number 5. You can get closer if you'd like, or you can just start pressing enter, because it looks like in this window there's only one intersection point. And when I press enter, I get my intersection point 3.6934. If you want, you can clear everything in the home screen and bring it back as an X value. You can even store it, except I don't need to store it because I don't need to figure out the answer. They just wanted me to set it up. So I'm going to say 3.6934. 6.3964. I got too excited. So this is 3.6934. Is that what it was? 6934. Yeah. This is what we're looking for. It said, write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Hey, I just figured it out. They just want the setup. They don't want me to figure out the answer, and that's okay. But the process is the same. Find the shape of the cross-section, find the area formula of the cross-section, find the area function of the cross-section, take the integral of the area function of the cross-section, and that's going to give you the volume. That's exactly what we did here in example 2. I'm getting a little excited here. So let's go to example 3. A little bit closer to our current year, 2014. Let f of x be e to the 2x. Awesome. Let R be the region in the first quadrant bounded by the graph of f of x and the vertical line x equals 1 as shown in the picture, in the figure below. Region R forms the base of a solid whose cross sections perpendicular to the y-axis are squares. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Oh, so now they've changed it on us. Now we're doing cross sections perpendicular to the y-axis. So that means my cross sections are going to go like this.
Tutorial has now come to an end. Please start making your way out of the building. Late buses will be arriving and leaving promptly at 5:40.
I do know, however, that my shape is a square, and that's nice because some things are familiar here. So the area of a square, just to remind you, is side squared. Now I'm looking for the area function of the square. Well, I got to be careful because if you look carefully, I'm stacking from the bottom up, right? I'm stacking like boom, 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 boom. And so in this first part between y0 and y1, in this section, if I'm measuring sideways, if you remember the videos about finding area, I need to do right minus left. Well, my right is 1, my left is 0. But once I get to 1, now my right is left, my 1 is right, and my left is the function, e to the 2x. So I have to build two separate integrals just like I did in the previous one. So let's see. Right minus left in the first part. Well, that's going to be 1 minus 0. And I'm going to square that. Seems kind of silly because we're using constants, but let's follow the process and set up the integral the way we've been doing it, which is we got to find the length of this cross section. And the length of this cross section is right minus left because I'm going to stack them in a way that they're horizontal instead of vertical, right? So right minus left, 1 minus 0. But then there's a second, or once I get over here, I have to do 1, because that's the right side, minus whatever the function is. Now, what was the function? The function was y equals e to the 2x. Except since I'm doing cross sections perpendicular to the y-axis, I need to rewrite this function in terms of y, right? So not in terms of x, but in terms of y. So right now, this function says y equals e to the 2x. I need to rewrite it so that it says x equals something in terms of y. So I need to move stuff around. How do I do that? Well, let's see. I could, and I will, take the natural log of both sides. If I take the natural log of y and set it equal to the natural log of e to the 2x. Why would I do that? Because the natural log and the exponential are going to undo each other. And when I do that, I'll be left with natural log of y equals 2x. And if I divide both sides by 2, well, then I'm going to get, that's not a -7, by the way, that's an arrow. If I divide by 2, I'm going to get 1/2 natural log of y, or natural log of y divided by 2 equals x. Now I have an equation that's in terms of y. This is going to go in here. You could also write natural log of y divided by 2, because we really did divide by 2 on both sides. I just took that division by 2 to be the same as multiplying by 1/2. Great. I found how to find the area of any square in this section and any square in this section. And they're built differently, right? So therefore, to find the volume equals the integral of this first area function setup, which is 1 minus 0. I guess I can just say 1. I guess I can just say, I don't even need to say 1 squared. I guess I can just say 1, but I want to leave it as 1. dy, because everything's perpendicular y, and this is the reminder that I need y values here. So y values starting at 0 and going to 1. And then we're going to add on the integral from 1 to the next y value, and that's going to be from 1 to e squared of this setup. And this setup was, and I'll put the dy, this setup was 1 minus 1/2 natural log of y. Right here, my good people, you have now set up an integral, or in this case, a sum of two integrals that will find the volume of this three-dimensional object that we create when we put cross-sectional squares in this orientation from 0 all the way to the top y value, and the top y value is e squared. Do we need to solve it? No. We just need to write but do not evaluate an expression, and that's what we just did. Always read the questions. Don't do more than you need to. But if you follow this process, it's a pretty easy setup to build that volume integral expression.